Hi, my name's Zach and this is my 4th year capstone project, Damage Detection in Beams by Acoustic Analysis. I was tasked to try and find damage in beams using sound. In order to do this, I needed to ask fundamental questions such as, what is sound? Through that, I find that sound is vibration, and that vibration is very easily modelled. Using the equation of motion, there's 3 properties of a beam which relate to its vibration: mass, stiffness, and damping. I'm particularly interested in using stiffness as a metric to measure the amplitude of vibration of a beam. This is as if there's a minor crack in a beam, its mass will not reduce much, but its stiffness will be greatly affected.
So now that we know we can use sound to measure stiffness, we have to ask ourselves, why would we want to do this? Structural engineers are constantly trying to find non-invasive ways to detect damage in beams. Ideally, they'd want to be able to find small cracks before they grow out to be more of a problem. What makes this project possible is harmonic resonance. It's known through various studies that the amplitude of vibration increases significantly when a force is applied to a structure with a frequency equal to or similar to the natural frequency of that structure. This phenomenon is known as harmonic resonance. Interestingly, if we know the mass and stiffness matrix of a beam, we can predict at what frequency you'd expect harmonic resonance to occur. This is as, if we look at the formula here, the frequency F is a function of stiffness K over mass. This essentially means for our 2 beams which are identical, they'll have the same mass, but the stiffness will be greatly different. The damaged beam will have a lower stiffness than the undamaged beam, so we'd expect a different natural frequency. And because we can measure the amplitude of vibration, we can figure out where this natural frequency occurs if vibration is induced at a bunch of different frequencies. Moving on to the prototype, it's quite simple.
Where we have a small unbalanced motor, and every time it turns, it goes to turn upwards, the mass ends up at the bottom and pushes the beam down. And it repeats this process. The prototype uses a high-speed unbalanced DC motor that is attached to the midspan of the beam to be tested. This makes the beam vibrate up and down with each revolution of the motor, meaning that the frequency of the motor is now the frequency of vibration for the beam. This is really great because it means that we can control the frequency of vibration for the beam using the motor. If we slowly speed up the motor and go through some frequencies from 30 Hz to 250 Hz, and we know that the natural frequency occurs at 100, if we do that and we see a spike in amplitude at 100 Hz, we can be pretty confident that we've found it. But otherwise, we can also use that to check if it's damaged and not exhibiting the behaviors of if it were structurally intact. Now we go on to the test itself. For the test, we used a square hollow section beam that you can see above, and was tested and subjected to an induced vibration from the motor between 30 and 250 Hz. An identical beam is also tested, but with reduced stiffness due to a 4mm notch that was cut in the midspan. We can see here with some of the results, we see an unexplained amplification of the sound recording here, even though it's still speeding up. We can listen to that sound recording now.
What you might notice with that clip is the unexplained amplification at around 100 Hz. Even though we continue to double the speed of the motor from here, which in turn will create more force on the beam and more displacement, which should result in higher amplitude. It takes some time before it gets to the same level as you've seen at 100 Hz. This in turn tells us harmonic resonance probably did occur around 100 Hz. This is further backed by the numerical calculations, which calculated the natural frequency for the first mode to occur at 106 Hz. A total of 10 tests were done, and 5 for each beam, which can be seen below in the graph. It can be noted that for the undamaged beam in orange, the natural frequency was always higher, with the exception of the last test. This is to be expected, as something with a higher stiffness should have a higher natural frequency. The decreasing accuracy of each subsequent test might be down to 2 main factors: the heat of the motor not being able to dissipate quickly enough between tests, and the bolts holding the fittings and fixtures on the supports together shaking themselves loose. In my conclusion, detecting damage with sound definitely has some promise, but there's a lot of work that needs to be done to improve the accuracy. For now, I'd just like to thank you for listening to my presentation, and ka kite and goodbye.